Another draft physics presentation. Anyway, yes, more interferometer stuff. Just thought I would update as I progress in this experiment. Um, so I used a piece of really thin plastic, just a piece of, like that's the plastic you get when you buy something and it's wrapped in hard plastic. So it's kind of a thin film, but it's not, it's kind of a rigid piece of thin film. Anyway, like credit card, but clear. Anyway, thinner than that, but anyway. So, and I got the same pattern for the straight line trip, the trip where you go through the beam splitter both ways. And it came out this way. So I'll play the video and such. And so forth and whatnot. So you can see it's a pretty good pattern. Trying to figure out. Well, here I'll wait till we get to the other side, then you can see. So there was the thin film. There's reflecting off that path, and then it goes sideways. And so I lined it up so these two were sort of right on top of each other, almost, pretty close. And there's pretty much no pattern. I mean, there's some artifacts that are from other things that are shadows, but there's no rings, on the other path, where it's basically only the path where it only goes through the beam splitter once. So it reflects one time and goes through on the second path, the second trip. And so that path isn't producing anything. And the two spots are pretty much on top of each other, so I'm just going to now block both sides. Block one side, then I'll block the other side. And you can see that there's no real difference in the scatter pattern. Obviously one side has more scatter than the other side, but other than that, there's no difference. So that's when both of them are blocked. There's just one, and there's two. So yeah, I don't know why I'm not getting more of, well, I'm not getting any kind of something. There's no evidence of the rings or the interference or anything. So that's sort of interesting. Because if it was happening in the atmosphere kind of thing, it should have been happening here. So again, this is back to the argument of what you're using to split the light is a big part of this experiment, and that's where whatever's happening is happening. It's happening in that piece of film. So I'm just showing that I'm blocking the light, and when I block it, it doesn't change much. And such, and then I'll just show, see, it's just a thin piece of plastic that I'm using to reflect the light and transmit the light, and it's working. The beam is quite even. The one that reflects versus the one that goes through, they're both about the same intensity. And again, the weird one is the beam that just goes straight through and then straight back. That's the one that comes back with the ringed pattern with the thin film. So I've eliminated, there's no diffraction gradient. There's no two layers of glass. So I've eliminated all that, and you still get the same ringed pattern with just a piece of plastic, and you send the light through it twice and you get the ringed pattern. So that seems to me to be evidence of something, something that needs to be explained. And I'm leaning towards an explanation that it's just it's this internal reflection thing. So just to verify where we are here, so it's this splitter source, and there's a mirror, and then a target over here. And the pattern that's creating the one that's getting the best ringed pattern is here behind the laser. So the laser goes through and through, and that's the one creating the best pattern, the consistent one. So the bit that reflected this way was just one of those dots that I turned on and off, and the bit that's going this way again was just one of those dots I turned on and off, no pattern. And they don't combine to make a pattern. So yeah, so the real point is that what I think happens is in any material, you know, so let's just make the material bigger. When the light hits, we're first off we're sending in a beam that's got a lot of rays in it. So there's a lot of entry points, and each one of those positions creates an internal reflection. And the key thing with the internal reflection is that the first reflection is a refraction. So it has that, you know, that broken angle. It refracts at the wrong angle, and then it starts reflecting normally inside. And at certain points, those internal reflections, if they hit the right spot, end up coming out as they get transmitted instead of continuing to internally reflect. And so this really has to do with the atomic structure of this medium. And in Newton's rings, yeah, you have a ratio where as you change the thickness of the glass, you know, you go from 0 to 16% reflectivity. So there's, when you make glass just the right thickness, none of the light reflects. So this is the other thing you have, is the reflections that are going down the other path. But I think the thing creating the pattern is this stuff going inside. And so when it transmits, let's I could have drawn that bigger, I suppose. It does its refracting, and then it refracts again as it comes out into the atmosphere, so it undoes its crookedness, and so these beams come out straight, that refracted. But the ones that come back through will also do that. They'll come out straight, but they've all been changed in terms of their separation, is what I guess I'm saying. So the internal reflection is essentially changing the separation between the rays of light, and the fact that it's also diverging it. So that's the other thing to explain, really, is, as you saw, the pattern on the door, okay, is maybe it's a total of, say, 8 feet from the laser, you know, the emitter, to the mirror. So it's a total of, say, 16 feet. And over that 16 feet, you went from a point laser to something that's at least, say, 15 inches across. So the pattern here is 15 inches across. So there's been a lot of divergence. And from this little, you know, whatever it was, 2 millimeter laser beam point. So the point goes through. When it comes back, it's still a point. It still looks pretty pointy. You know, anyway, from, you know, it's kind of like impossible to have it reflect and then be able to put a target in there and actually see what's getting produced by the reflection. But the reflection looks like it goes right through the beam splitter. So it doesn't get diverged on this path. So this path isn't diverging. So the reflection comes in is still a relatively small point. And then somewhere in the last leg is when this happens, this huge divergence. And you know, this is only whatever 3 feet from the laser, from the beam splitter to the door, let's say, is 4 feet. So in that 4 foots in that 4 feet of distance, you have a huge spread here for some reason that I don't have a perfect explanation for. But it's happening inside the beam splitter, I guess is the argument I'm making. So when you put more than one source of light, I just flip this over maybe. Yeah, that might be good enough. So the trick is, let's see, just to draw it. as cleanly as possible. So the laser goes in this big, it reflects, comes back, it's still only this big, and then when it comes out this last leg is when it's spreading. And so I guess the point would be is these two beams are hitting the same point. So this beam is going through the same place in the beam splitter as this return one. And because of that interference, that head-on collision or whatever you want to call it, that's doing something to the material that's causing this diffraction. And to create this very even, very symmetrical. I mean, these, it's very symmetrical in that it gets tighter and tighter as you go further away, and the dark spaces seem to be the same thickness, and it's the light parts seem to get a little thicker here at the base. But anyway, so that's to be explained, and I don't have an explanation off the top of my head, besides the fact that this is energy going into a piece of material, and that's probably disrupting the electrons, and then the light going through the first time is disrupting the electrons, exciting them, and then this light's coming through these excited electrons, and that's what's causing this interference, which isn't really interference, it's just changing the path of the light, because you're changing the reflective index of the material by shooting a bunch of energy into it. But I guess I would still argue that it's fundamentally has something to do with internal reflections inside of the material. That's probably what creates this. That's probably what creates the fact that the rays are separated. The fact that they're diverging, I think, has to do with the disruption of the electrons by the beam going through the same place in the material twice. It's going through some place that's already being energized. So the trick might be, I mean, if you could pulse a laser fast enough where you wouldn't have any, by the time the light reflected, there wouldn't be any light coming in, that would be really interesting, but I don't think they can pulse a laser that rapidly, unless you made these distances really long. So that might be interesting to see if you let the plastic quiet, go, nothing's in it. When the second beam comes back, there's not a beam still going through one direction. Then you might have, might be some indication that it's just happening inside the plastic, but obviously that's not something I can create. So I can't do that experiment. So anyway, that's where we are. I don't know what I'll try next. Don't know what to do with it, but it verifies what I was saying, is that this pattern isn't being caused by the kind of interference people think it is. It's not photons interfering with each other in the atmosphere. It's photons interfering with each other in the splitter. Because again, this pattern was created without any interference from the other one at all. It has just no effect on this pattern. You don't need the other arm to create this pattern. So that's where we are, and such. I think that's all I had. Probably something I forgot to mention, but anyway, till next time, and such.